Hello students, welcome. Previously, Form 4, Topic 2, we are dealing with Lesson 4, Determination of Enthalpy Change. We have done number 1, that's molar heat of solution. In Lesson 5 today, we are going to do number 2, that's molar heat of combustion. So let's start by first of all defining what heat of combustion is. So heat of combustion is the enthalpy change that occurs when a substance is completely burned in oxygen. Molar heat of combustion is the enthalpy change that occurs when 1 mole of a substance is completely burned in oxygen. So if you can define heat of combustion, you also know how to define molar heat of combustion. So you only change here when a substance, you just put when 1 mole of a substance is completely burned in oxygen, if you want to define molar heat of combustion. Let's go examples. Example 1, we are told when 8.0 grams of sulfur is completely burned in oxygen in a calorimeter, the heat evolved raises the temperature of 500 centimeter cube of water by 35 degrees Celsius. Full stop. Calculate the molar heat of combustion of sulfur. In bracket, we are given the specific heat capacity to be 4.2 kilojoules by kg per Kelvin, and we are told the relative atomic mass of sulfur is 32. So if we want to do molar heat of combustion, the steps are just the same to those when we are dealing with molar heat of solution. The first step, we are supposed to get the enthalpy change. Enthalpy change is given by mc delta T. So we said we said enthalpy change is given by mc delta T. We said where m is the mass of the solution. Here we are given the volume of the water, and that volume we are going to convert it into mass by multiplying the density of the solution, which is given 1 gram per centimeter cube. So the centimeter cube go with centimeter cube, we are going to get 500 gram as our mass of the solution. The specific heat capacity is given as 4.2, and the temperature change here is given 35 degrees Celsius. So let's just try to have the formula. The formula is enthalpy change is given by mc delta T. So our m here, as I've said, it is 500. We are having 500 centimeter cube. You only write 500. It seems 500 gram. You multiply by 4.2 as our specific heat capacity times 35, which is our temperature change. So we have to divide by 1000 so that we make our enthalpy change in kilojoules as it is unit. So this will be equal to 73.5 kilojoules. 73.5 kilojoules. So that's the first step of getting the molar enthalpy of combustion for this sulfur. Next step, we have to get number of moles. So moles is given by mass over molar mass. Okay, the mass given here is 8.0 grams of sulfur divided by the RFM of sulfur, which is 32. So here we are going to get 0.25 moles. 0.25 moles. Okay. After that, we are going to proceed to molar enthalpy of combustion, and we are going to say this number of moles produces this amount of heat. What about 1 mole? So 0.25 moles produces 73.5 kilojoules. What about 1 mole? So we are going to say 1 times 73.5 divided by 0.25. Here we are going to get 294 kilojoules per mole. So let's see whether this reaction is endothermic. If it is endothermic, we are going to put positive here. If it is exothermic, we are going to put negative there. And that one will be shown by the temperature. We are told that the heat evolve rises. We said if you hear rises, that means it's an exothermic reaction. If you see drops, it will be an endothermic reaction, so it will be a positive. So our answer will be negative 294 kilojoules per mole. So we are going to go to example 2. And in example 2, we have in an experiment to determine the heat of combustion of methanol. Methanol is written CH3OH. A student used a setup like the one shown in the diagram below, this one here. We are having the volume of water, 500 centimeter cube, the final temperature, the initial temperature, the final mass of lamp plus methanol. It is 22.11 gram. Then initial mass of the lamp plus methanol, we're having 22.98 gram. The density of water is 1 gram per centimeter cube. The specific heat capacity is 4.2 kilojoules per kg per Kelvin. So the question that we are asked is, let's go to the other page. The first question we are told, write an equation for the combustion of methanol. So how do we write methanol? We have said methanol is written CH3OH. Methanol is liquid. All alkanols are liquid at room temperature. It reacts with the oxygen. Here we are going to get carbon dioxide, which is gas plus water or steam, whichever you like. So to balance it, we are going to put 2 in the side of methanol, and we are going to put 3 in the side of oxygen. We are going to put 2 and also 4, like that. So this equation will be balanced if you put 2 in the side of methanol, 3 in the side of oxygen, 2 in the side of carbon dioxide, and 4 in the side of water. Next, we are told calculate from here on the number of moles of methanol used in this experiment, the number of moles. So if we want to get the number of moles, we have to get first of all the mass of methanol. And check here, we are having final mass of lamp plus methanol to be 22.11 gram. And we're having the initial mass of lamp plus methanol. This is 22.98. So first of all, we have to get the mass of methanol. Mass of methanol is gotten by the initial mass of lamp plus methanol minus the final mass of lamp plus methanol. So mass of ethanol will be, it's not ethanol, it's methanol, will be equal to the final, the initial, which is 22.98 gram minus the final, which is 22.11. Here we are going to get 0.87 gram of methanol. So next, let's get again the RFM of methanol. So this will be equal to 12 plus 1 times 3 plus 16 plus 1. This we are going to get 32. So how are we going to get moles? Moles is given by mass, which is 0.87, divided by the molar mass, or the RFM, which is 32. So in our case here, we are going to get 0.02719 moles of methanol. Okay, the next question, we are told the heat of combustion of methanol. So for us to get heat of combustion of methanol, we are supposed to have our formula, enthalpy change is equal to MC delta T. So our M in our case is 500 because the volume of water given was 500. So if we convert that one into mass, it will be 500 centimeter cube times 1 gram per centimeter cube, which we are going to get 500 gram times the specific heat capacity, which is 4.2, times the temperature change. So here the temperature change will be 7 because I'm having 27 to be final and we are having 20 as the initial. But check here, there is a rise in temperature. That means this is an exothermic reaction. But the temperature change there is 7. So 7. So we can write somewhere here, temperature change will be equal to 27.0 minus 20.0, which will give us 7.0 degrees Celsius. Okay, divided by 1000, so that we will convert our answer into kilojoules. So I'm going to get 14.7 kilojoules. Okay, so next I'm asked the heat of combustion per mole of methanol. The heat of combustion per mole of ethanol means the molar enthalpy of combustion of methanol. So we are going to say this number of moles, that's 0.02719 moles, produces this amount of energy, that's 14.7 kilojoules. So we ask ourselves, what about 1 mole? So we are going to get 1 times 14.7 divided by 0.02719. Here I'm going to get 540.64 kilojoules per mole. So next, let's see the sign there. So as we have said earlier on, there is a rise in temperature. The initial temperature was 20, but final temperature was 27. That means this is an exothermic reaction. We said an exothermic reaction is a reaction that's accompanied by the production of heat and it results in an increase in temperature. So we are going to put negative because it's an exothermic reaction. So next we are going to go to draw the energy level diagram for the combustion of methanol. So to draw the energy level diagram, we are supposed to draw first of all our axis on the y-axis and the x-axis. So we are going to sketch. I'm having the y-axis and we're having here the x-axis. Okay, here x-axis we are going to write reaction path. We are going to write reaction path, and in this other side we are going to write energy. This is energy. Remember, energy is measured using kilojoules. So this is an exothermic reaction. It's an exothermic reaction, and we said in an exothermic reaction the reactants are having a higher content, a higher energy content than the products. So our reactants are methanol, which is liquid, plus 3 of oxygen gas are our reactants. So our products, the products we are told in exothermic reaction, they're having a lower energy content compared to the reactants. So we're going to have carbon dioxide and 4 mole of water, and the air comes from the reactants and goes towards the products, and we're having the enthalpy change here to be negative 540.64 kilojoules per mole. So that's our energy level diagram. So next we are going to go from here C, we are done. Next we want to go to Romeo D. In Romeo D we are told explain why the value of the molar heat of combustion obtained in this experiment is different from the theoretical value. Even this one we have done it in molar heat of solution, and that's due to the experimental errors. The answers are just one and the same. So one is we say some of the heat energy is lost to the apparatus. Some of the heat energy is lost to the apparatus. That's one point. Then second point, we said some of the heat energy is lost to the surrounding. So number 2, we can say some heat energy, some of the heat energy is lost to the surrounding as well. It's lost to the surrounding, which is not accounted for in the calculation, making the value of the molar heat of combustion of methanol obtained in this experiment different from the theoretical value or the ones that are quoted in data books or in our textbooks. So we go to example 3. In example 3, we are told 1.26 grams of element Q was completely burned in oxygen or in air. The heat evolved was used to heat 250 centimeter cube of water, raising the temperature from 32 degrees Celsius to 50 degrees Celsius. So I will calculate the relative atomic mass of element Q, given that the molar heat of enthalpy of combustion is negative 360 kilojoules per mole. So here we are supposed to get the relative atomic mass of this element Q. So the first step, I have to get first of all the enthalpy change. I can get the enthalpy change because I have been given the volume of the solution, so that I can get the mass of the solution or the mass of the water. Then I can get the temperature change, and I also have the specific heat capacity in the bracket. So I can get first of all enthalpy change. So let me get first of all the temperature change. The temperature change here will be 50 minus 32. Here I'm going to get 18 degrees Celsius. That's the temperature. Mass, I can get the mass, and I can say mass is given by volume, which is 250 centimeter cube times 1 gram per centimeter cube as the density of the water, giving me 250 grams of water. So I can take the formula, that's enthalpy change is given by MC delta T. So my M is 250 times my C is 4.2, then my temperature change is 18 divided by 1000, so that I convert my answer into kilojoules. So I'm going to get 18.9 kilojoules. Okay. So next I'm supposed to get the number of moles, but I cannot get the number of moles, although I have the mass of the element Q, but I don't have the molar mass of the Q. That's what I'm going to look. So I have to get the number of moles on another way. I know I've been given the molar enthalpy of combustion to be 306 kilojoules per mole. So I say 1 mole produces 360 kilojoules per mole. I'm not supposed to take negative. This negative is only showing me whether the reaction is exothermic or endothermic. So this heat energy, what amount of moles can it give me? I cross multiply. 1 times 18.9 divided by 360 will give me the number of moles to be 0.0525 moles of element Q. So if I'm having this number of moles, I can get the molar mass, because moles is given by mass over molar mass. That's the relative atomic mass. So the moles is 0.0525. It will be equal to the mass of element Q, which is 1.26 divided by X, which I don't have, which is the relative atomic mass of Q. So to get X, it will be equal to 1.26 divided by 0.0525. X will give me 24. So that is the relative atomic mass of element Q. We have gotten 24. Okay, next we are going to go to the extended question. We are having around 3 questions. You can try to attempt it. That's the end of our lesson today.